Good afternoon, and welcome to this afternoon session. This is monitoring on a landscape scale. So this afternoon session will explore the use of UAVs in peatland monitoring and the role of peatland mapping in accelerating peatland restoration in Northern Ireland and mapping across England. So first of all, our first presentation this afternoon comes from Dr. Ben Clutterbuck of Nottingham Trent University and Dr. Adrian Yallop of Cranfield University. So a bit about those two. Ben is a senior lecturer in GIS and remote sensing at Nottingham Trent. He's got 16 years experience in the application of geospatial technologies in the field of environmental monitoring at a landscape scale. And Adrian, with degrees both in ecology and remote sensing. Adrian has oddly found himself working as a remote sensing ecologist for the last few decades. He arrived in Moors of the Futures bog via research on mine clearance in the Falklands, humic DOC in Yorkshire, BAP mapping, salt marshes and quantifying fire management across the whole of England for clients ranging in the UK government to DEFRA, Natural England, British National Space Centre, CEH and the water companies. So without further ado, let's go over to the first presentation of the day.
Hello, thank you for inviting us, and thank you everybody at More to the Future, particularly Tia and Dermot and the field teams that have undertaken extensive field survey for this project. So the research that we're going to present today forms part of the Moors of the Future Partnership More Life 2020, and this project is looking at conserving and protecting blanket bog in the South Pennines Moors Special Area of Conservation. Now Adrian and myself and colleagues have been working with Moors of the Future over the past 4 years, and we've been looking at one component of this to monitor the impact of conservation actions on a landscape scale using an unmanned aerial vehicle. So we've only got 10 minutes, so we're only going to be able to give you a quick overview of one aspect, and that is mapping blanket bog species. We need to map species in order to be able to monitor them so that we can look at change. So the South Pennines Moors SAC in the top right, you can see the extent here, it's around 650 square kilometres, and we have 5 study sites and they're located fairly centrally. The most northerly site, Moss Moor, is up by the M62, and towards the south there is a site on the Kinder Plateau. Now you'll have to ask Moors of the Future about the names of some of the other sites. I've certainly never seen a penguin at this site. So let's look straight at some data. I'm sure many people have seen UAV derived imagery. Here's some colour imagery from a UAV. We can certainly see, because of the high resolution, we can see blanket peat. We can actually see cracks in the bare peat. We can see individual rocks. But of relevance here, on the right hand side, we can see individual plants. But from a photograph, how do we know what species they are? We've got some very green vegetation here. It's in a gully, it looks quite wet. It's probably a bryophyte. It could be sphagnum, and it could be polytrichum. And there's some tussocky looking vegetation here. Now this could be cotton grass, Eriophorum vaginatum. There could be some Juncus in there. We can't reliably map a species from an image. The only way we can do that is with ground observations. So we need to go to the ground, identify a species, record the location with differential GPS so we know where it is to within 2 centimetres. The next thing we need, well, we're not going to map by hand from a colour imagery. We want multispectral data. This enables us to undertake image classification, and if we have multispectral data, the imagery must align with the ground truth data. So if the ground truth are accurate to 2 centimetres, same again, we need 2 centimetre accurate multispectral data. So in August 2018, a UAV was flown over the study sites and 2 independent sensors were used, collecting colour data on the left, which you've just seen before, but let's have a look again, it's great, up 2 centimetre resolution. And on the right you'll see multispectral data that were collected. You'll note the resolution is slightly lower, that's just the nature of the sensors. The important thing about both of these data sets though is that they corrected, in image processing, the auto correction accuracy was on average plus or minus 2.2 centimetres. So we know if we collect data in the field, we can pretty much pinpoint it to the pixel in the data. Now we've got to hold our hands up. We didn't just use UAV data. Some of you might be interested or perhaps even surprised that the image on the right hand side is not from a UAV, it's actually from an aircraft. That's a conventional aerial photograph, 5cm resolution, red, green, blue and near infrared, so perfect for image classification. So for the project we have imagery for 3 years, 2018, 2019 and 2020. This is where we now have to thank More for the Future again, because the word extensive is going to reveal itself shortly. So the team of field assistants from More for the Future visited each site. They identified single stands of species that were ideally more than 50 centimetres in diameter, and they collected 7,104 samples, vegetation, but also bare peat, mineral soil, rock and water. And that comprises 61 classes, which includes 10 sphagnum species. It's worth noting that this took between 13 to 16 days per site, so it's not a small undertaking by any means. And how would that look? Well, this is a square kilometre, and each of those points were visited by the team. In a square kilometre, it's about 1,300 samples. So this is a perfect data set that we were then able to use to classify the imagery. Let's have a look. So on the left we have the aerial, the aerial photograph or the UAV image, and on the right we have a classified product. Now there's similar shapes. Let's have a look. So this is where the bracken is, and classification said it's bracken. This is where the bilberry is, and yes, that's been classified as bilberry. This is heather, and the classification says heather. Excellent. So now we can look at change over time. We've got species for each year, I think. Or can we? Adrian?
Thanks, Ben. Okay, as Ben has shown you a fraction of what we've been doing for the past 1,000 years now from More for the Future. And this is another example, kind of outputs that we're producing from UAV imagery, image on the left and the classified product on the right. I chose this because it's particularly pretty. I like the purples. And the legend on the left, you can see obviously it's a Kaluna dominated environment. So yes, we've been producing some pretty good looking pictures. And that's not too difficult in remote sensing, actually. It's kind of passing grade maybe. But sadly, it's all too common an endpoint to so-called remote sensing projects. But is this actual data? Can you actually use it for anything? Can you trust it? Or is it just for hanging on the wall, the office, or maybe the foyer, trying to impress people? Well, because of all the field work undertaken by More for the Future, and thank them, we can find out a considerable amount about this classification process. So not only do we collect training data, we also collect extra field data for use in error assessment, and from that we create a confusion matrix. Okay, this might well confuse you. I apologize if it does. And I know you're going to say all the thing, yes, I can't read this, it's all too small. Why do people put small print on things? Yeah, I'm sorry. We haven't got time to go through all the details anyway, because of the short time we have. What it does basically is show how accurately each species has been mapped in the image. And from that you can produce an average. Now in this case the overall average was 45%. Wow. I hear you say, well I don't, but anyway, only 45%. Isn't that terrible? Well, not at all, and I'm going to explain why. Firstly, of course, we actually know. If we hadn't done that, the client could have assumed it was perfectly 100% accurate and spent loads of money on restoration, just on a pretty picture. Secondly, it shows which classes are mapped well and which aren't. Now that can help guide your restoration planning as well. You won't base it on things that map inaccurately rather, and you could base the product well on the ones that have done well. And thirdly, from this project status, the most important aspect is that we can use it to drive forward and modify the project objectives for the future, which is what we're currently undertaking. We can do a number of things as well as this. We can do separability analyses, Here's a Jeffrey Machishita. Basically, look, we haven't got time for this. We've been given 10 minutes. I'm sorry. Look at the colours again. It always works. Green, good chance of separability. Yellow declining. Orange, yeah, not getting so good. And the red, you aren't going to separate them. So it gives you a guidance again. Another way we're using now is ordination analysis in multispectral space of the species. It shows us which ones, basically in this kind of picture interpretation of this, is that those that are farther apart, like the Areophrum up here, if you can see my mouse cursor moving, probably you can't, is going to well separate from things like flagstones, which by the way is a path the other side. They're going to separate well, but it isn't going to separate well from Descampsia. Okay, so that is another useful thing to guide where it goes. So current and future, right. Now we know which species can be differentiated and those that cannot. We're working iteratively with more to the future to develop species groupings. Now the idea of this is that we'll have those that map to the highest accuracies achievable, but still contain sufficient information to more to the future for monitoring and planning. Okay. Now there's going to be a trade-off between these two things, and hence constant liaison backwards and forwards with more to the future to decide, yep, we'd like that, but we'll accept lower accuracies. Yes, we take the higher accuracies, but we get a bit less information. So really, that's all we have time for today, children. Sorry about that. It wasn't my choice. If you want to know more, there's a few seconds for questions, but obviously we don't want to hog all of that. And well, it will be, yeah, I'm sorry we couldn't meet up normally for a few beers afterwards. That makes conferences worthwhile. Thanks, guys. Cheers.
And thank you to Adrian and to Ben for that whistle-stop tour of the work they've been doing with over eons with Moors for the Future. So from the South Pennine Moors, we fly across, because we're talking UAVs, off to Chris Osborne and the Yorkshire Wildlife Trust. So Chris is the remote sensing officer and GIS officer for the Yorkshire Peat Partnership and for the Pennine Peatlife projects too.
Hello everyone, my name is Chris Osborne. I'm the GIS and Remote Sensing Officer for the Yorkshire Peat Partnership and Pennine Peatlife. And in this talk I'm just going to briefly go through how useful UAVs are for monitoring peatlands. So just for some context, UAVs are unmanned aerial vehicles, also known as drones, and they come in two forms, fixed wing and multi-rotor. Now in terms of data, I'm just going to focus on the RGB data sets that can be acquired from UAVs. You can collect multispectral or LiDAR data using other systems, but for the sake of this talk, I'm just going to focus on RGB datasets. So when it comes to a survey, we run transects over an area of interest and collect dozens or hundreds of RGB images, and we can stitch these together to create these really great detailed overview images. Now resolution tends to be between 1 to 5 centimeters, so as you can imagine there's a lot of detail, a lot of information in these images, which is fantastic for firstly understanding what you're up against when it comes to restoration, but also observing how your restoration is going. From this dataset we can also create surface models. Now these datasets are fantastic for understanding hydrology and erosion features, so things like gullies, hags, grips, they show really well in these datasets, and it's a fantastic tool for monitoring surface change or hydrological changes. Now in terms of applications, I'm just going to run through a handful. So firstly bare peat, then a research example, and then finally hydrology and surface change. So with bare peat we use supervised classifications, and we can create these outputs in very quickly and consistently as well, particularly when you compare this to manually digitizing these features. And we're able to quantify change and restoration success over time. So in this example, this is hardly common in the North Pennines. Now before we started restoration, we collected the data and quantified the amount of bare peat. Then once restoration had taken place, we were able to observe areas of bare peat but also brash. And then this gave us an extra level to observe where we're hoping to see revegetation. So a year later, with this image, you can see areas that have started to revegetate. And this has been a fantastic application, firstly to understand where we're seeing some success, where the revegetation is happening, and we're also able to quantify that. But also we can observe where things aren't really working as well as we would hope, so we can see the success, but also where things aren't working. And it means that we can focus our efforts a lot better going forward. Now, in terms of our research, we have a trial of sphagnum inoculation methods, and these plots are at a very fine scale, they're very small, and the multi-rotors have really shown their advantage in this application as they're able to fly very low, so they can hover very low to these plots, and with the stabilized camera they can get some really high quality images. And if we compare a base to an after treatment image, we can run image classification techniques to extract features such as sphagnum, and then going forward in subsequent years we can observe the potential, hopefully, the growth in these sphagnum clumps. And we'll also be looking to see how this compares to ground-based methods as well, to see if this is a more efficient approach. Now, in terms of hydrology, I'm going to focus mostly on interventions. Now, if we just take a before and after shot, we can see quite a nice, success example, really. A big impact in these peat dams with the retention of water. If we want to analyze that further, what we can do is we can extract the image within a gully system, and then firstly observe the baseline, and then in this case, when stone dams have been placed, we can firstly extract those stone dams so we can monitor their structure and their integrity going forward. But also we can observe the amount of water that's been retained within this gully system thanks to those stone dams. And coming back a year later, we can see an even further increase in water levels. So it's a fairly simple and quick way to monitor the amount of water that's being retained in these systems and the success of our restoration work. Now, another thing we're working on is looking at sedimentation build-up within gullies, particularly with the placement of interventions. Now, this 3D image is before any interventions have been placed, then when they've been placed, and then after. So we have a set of 3 temporal data sets, and it's worth noting that these have been normalized, and we're looking at relative surface change. Because we don't have access to highly accurate differential GPS units, we're not able to observe absolute change. So in this case, what we've done is we've subtracted the baseline from the year after interventions have been placed, and in this case we can see there is an increase in the surface level, relative surface level within the gully channel. So it gives us a good understanding of potential sedimentation. Now, as I've mentioned, this is in development, so there is extra work needed. We're going to be looking at scaling this up further to larger restoration areas and also doing some ground truthing as well. But there is some potential in this. Now, with all those applications in mind, it's worth considering the barriers. One of the main barriers being weather dependency, so drones aren't able to operate in wet and windy conditions, and we operate mostly in the uplands of Yorkshire and North Pennines, so as you'd expect, a lot of the time it is wet and windy, so that does restrict us quite a bit. Another thing is access, so things like breeding bird season, but also many of our sites are owned for grouse management, so there can be restrictions in terms of if there's a shoot on, or landowners sometimes don't want us on. So these coupled together to really, it can restrict us. We're not able to get out and monitor at the time we would really like to. It's also worth mentioning that if you are looking to adopt a UAV for monitoring approaches, you need to have some considerations for data management. So you're going to be collecting gigabytes worth of data, so you need to make sure you have the capacity to effectively manage and store that, and also you need computers that are powerful enough to handle the processing and the analysis. And it's also worth just mentioning that ideally you want to have the dedicated staff to be able to get the most out of the analysis and the surveying with UAVs. Now, as we're talking about the usefulness of UAVs for monitoring, I thought it would also be worth comparing them to another remotely sensed data source, so satellite data. Now we're going to focus more on the open source datasets like Sentinel-2 and Landsat-8. It's also worth mentioning that I didn't include the manned aircraft data source. This is primarily because their data capture is quite limited in that it can be between 3 to 5 to 8 years. And so when it comes to monitoring, that is quite a restriction. So this is again hardly common, and if we wanted to take that same approach we took with the UAV to observe bare peat, what we could do is we could look at an NDVI image, but as you can see, the coarse resolution really has affected the amount of detail we can observe. Now if we're thinking about a very broad landscape approach and we're just observing areas, say, of actively eroding clusters, the satellite dataset works very well. We can see it's really observed Hartley Commons eroding area very well. But if we want to dig a bit deeper, it's not really possible. You would need to take that UAV if you want that finer approach. In addition, if we're looking at broad habitat types, so changes in woodland, heather grassland, acid grassland, satellites are a great tool for this. They're a lot quicker to process, not needing to get out and survey. We can just get the data from sources like Google Earth Engine, so this can be very quick to run. And also when it comes to things like burns, we found it to be very effective where we create NDVI images from before, during and after the burning season, combine them together into a temporal dataset, and then extract areas of new and old burns. Now we could do this with a UAV, but comparing the workflow with the satellite, this can take us between 15 to 30 minutes compared to those days of surveying with a UAV. So a lot more efficient to use satellite for these much larger, broader landscape scale monitoring. So just to summarize, if you're looking at monitoring with a remote sensed data source, really you want to consider what scale are you looking at. If it's the fine scale, absolutely a UAV is the way to go, but at these very broad landscape scale approaches, satellites can actually be good enough. And it's also worth considering as well that ideally, if you combine the two together, it's a very powerful tool set to have. So really that's a great practice if you're taken advantage of both of these platforms. So that's everything for me. So thank you for listening. I'd also like just to make note that there are some UAV webinars that we've done which delve into a lot more detail on the processes and the techniques that we've used and some of the lessons we've learned. So if you are interested in a bit more detail, I'd recommend going to the North Pennines website. Thank you.
Many thanks to Chris and the team up at YPP for that presentation. Now from the Northern Pennines, we fly across to Northern Ireland. Our next presentation about accelerating restoration, mapping peatland in Northern Ireland, comes from Matt Aitkenhead of the James Hutton Institute and Dr. Ian Garner from Ulster Wildlife Trust. So Matt is a soil scientist working for James Hutton Institute, focusing on the area of overlap between science, policy and land management. Ian is an ecologist and environmental scientist, and he leads Ulster Wildlife's Peatlands innovation work, which is currently delivering a programme of work that will provide insights and innovative options that will accelerate peatland restoration in Northern Ireland. So without further ado, let's move on to the next presentation, please.
Hello, my name is Matt Aitkenhead, and I'm going to present to you on the project of accelerating peatland restoration in Northern Ireland. The project is led by Ulster Wildlife and funded by Esme Fairbairn Foundation. Other partners include DAERA, the Department of Agriculture, Environment and Rural Affairs in Northern Ireland, and myself at the James Hutton Institute with some of my colleagues. We've been talking to a range of stakeholders, including landowners, farmers, public bodies and NGOs, so there's a lot of different people involved. The plan of the project is to inform policy and strategy towards peatland restoration in Northern Ireland. Currently, Peatlands and peat soils comprise about 18% of Northern Ireland's land area, but approximately 88% of this needs restoration and protection in some form due to degradation. This leads to a large amount of the release of greenhouse gases and loss of biodiversity. Now, there's quite a bit of urgency in this due to both the climate emergency and policy goals for peatland restoration in Northern Ireland. We also want to support the draft Northern Ireland Peatland Strategy, which is a document that's been out for consultation recently. The project outputs and impact aim to provide, firstly, a peatland map for Northern Ireland, and also information for a strategic approach to peatland restoration in Northern Ireland. We're aiming to provide recommendations for targeted peatland restoration work and to provide the scope for establishing a future peatland partnership. We also want to identify barriers to progress from the perspective of landowners and farmers. We want to help break down the perception that non-active farming in Northern Ireland is somehow secondary to active farming and demonstrate to land managers that mitigation and adaptation actions that they can carry out will actually improve their future income. We also want to allow farmers to be able to demonstrate to people in urban areas that the activities they're carrying out, including peatland restoration, will actually provide benefits to them. So there's a lot of pressure on agriculture in Northern Ireland to reduce greenhouse gas emissions, and what we want to provide farmers with is a way of actively reducing the greenhouse gas emissions while taking time to be able to change the other aspects of their farming. We also want to be able to mitigate against the risk of future legal challenges from people that have said, you've had the evidence that you're causing damage and you didn't do anything about it. So we're going to use a digital soil mapping approach incorporating multiple spatial data sets, including the ones that you see here, to create maps of peat presence and absence, soil carbon stock, and peat condition on the surface. These data sets have been chosen because they are important in terms of soil formation. They all come in different spatial resolutions, they have different projections, and so there's quite a lot of work in just getting the data together so that it can be integrated to produce the mapping. Once we know where the peat is, we then move on to finding out what condition it's in and whether or not restoration is possible if it's necessary. So we're going to look at the different conditions that it can be in, and you can see two examples here. One on the left, where there's a drainage channel that's probably quite easy to restore by ditch blocking, and then one on the right, where we've got a much bigger challenge, and we might be questioning the feasibility of it. In terms of the practical aspects of peatland restoration, I'm giving you an example here, which is the blocking of ditches. So these drainage channels that have been put in place to lower the water table in peat will then be blocked, and what happens there is the water doesn't drain away, so it fills up the drainage channel and stops draining the surrounding land. This means that the water table rises and also becomes more stable. Once the water table is within a certain distance of the surface, this means that peatland vegetation can regrow, and then that starts the process of peat accumulation and carbon storage. But what if you can't afford to restore all of the peat? In Scotland, the government has committed to restoring 250,000 hectares of peat by 2030 at an approximate cost of £1,000 per hectare for the restoration and the maintenance of the restoration. In actual fact, this will only pay for 8 to 10% of all the degraded peat in Scotland, because there's a lot more than this 250,000 hectares. So what the Scottish Government is trying to do, funding through CXC, is to identify the places where they can have the most effect through this restoration. In practical terms, this means where are the emissions highest and where will the restoration be most effective. In Northern Ireland, what we're trying to do is duplicate this work. In order to carry out the digital soil mapping, we need ground data. So what we're doing is we're sending a field team out, not to the thousands and thousands of points you see in the top image, but to some carefully selected field sampling locations in the lower image. We've used a stratified sampling approach to identify where those locations are that provide the greatest variability across all of the different soil formation factors that we're interested in. The field sampling involves sampling of the soils, the depth of the peat, and also taking samples for future analysis, and also ecological habitat description using a standardized approach that's been agreed with different organizations so that we're providing useful data for future work. Here are some photographs from the field team out in action, and you can see that the peat depth sampling rods that they're using have to be quite long. Some of the bogs that we've been finding are several meters deep, and sometimes they're having to work under fairly difficult conditions. Some of the sites that we selected actually turned out to be impossible to get access to, or were not in an ideal location. There's been some times that they've been, the sites are in the middle of a road or turned out to be on the edge of a quarry or something like that. So what we've been able to do is to identify new locations that are nearby which satisfy the same criteria. In terms of mapping peat condition, we're hoping that we can use remote sensing to detect features in the landscape, such as drainage channels or degradation features. We're using Sentinel-2 imagery for this, and we've managed to achieve a nearly 100% cloud-free mosaic. Once we've mapped the peat and the condition it's in, then we move on to identifying the low-hanging fruit. This will be the areas that have large current emissions and good chance of restoration success and emission reductions. We're going to prioritise large areas that have easy access because they make more economic sense. We're also looking for areas where there are multiple additional benefits as well as the carbon emission reduction. There's a couple of X factors here that are important in terms of success. One is landowner buy-in. So we're putting quite a lot of effort into engaging with farmers and the Ulster Farmers Union. Another one is policy support and making sure that the policymakers want to achieve this and that they see the benefits of it. In terms of additional benefits to greenhouse gas emission reduction, what do we mean? Well, there's a good example here in terms of erosion reduction. If this point at the top of the hill had been restored, then there's a high probability that you wouldn't have ended up with all the problems that have happened when the peat just decides to suddenly slide downhill and take everything else with it. Another benefit is improved water supply to urban and rural areas. In upland peat areas that are restored, there's better water retention, water storage in rainfall events, and that means that the base flow is more consistent during drier periods. This obviously provides a benefit in terms of water supply to different communities. Peatland restoration also reduces the risk of flood and fire on peat bogs. In terms of flood, restoration means that you've got improved vegetation cover and improved infiltration. So instead of running off down the hill, rainwater tends to enter the peat bog and stay there. In terms of fire, you've got a higher water table, so the peat is obviously harder to set alight. There are important biodiversity benefits to be gained from peatland restoration. This is a quote that I've taken from the Valuing Our Peatlands report, and I've highlighted text where they've said that there will be important benefits to nature from specific areas where restoration can take place. So, in the long term, we agree that systemic changes are needed, but farmers do need to keep making money. There's a quote that's popular amongst farmers in Scotland that you can't be green if you're in the red. We also know there's no silver bullet. There's no point in waiting till 2050 and then reducing the emissions by the stated 82% in agriculture in Northern Ireland, because there might be no technological solution that comes along. It's too much of a risk to take. So what we really need to be doing is trying to find ways to reduce the emissions by a set amount every year. In the long term, there are no non-radical pathways left. This significant reduction is going to be fairly radical over time, but either we change the system or the system changes us. Now, peatland restoration can help provide these reductions in emissions while the rest of the agricultural system adapts over time. And agriculture itself can be seen as a microcosm of the larger challenge within climate change, that of reducing emissions while avoiding inequality and the loss of livelihoods.
Thank you to Matt and to Ian for that. So before we come on to our last presentation of this session, just a quick word to say questions and answers will follow this session, where we've got all the presentees today willing and able to answer your questions. So please add them in or vote for your favourite ones, and we'll try and get through as much as we can in the time we have available. So our last presentation today comes from Andrew Webb of Natural England. Andy's going to talk about the landscape scale peat mapping in England that's working on at the moment. So Andy's Natural England's project lead for this. He's been doing this role since Christmas, so relatively new to peat, but he has worked on one or two peaty projects over the last couple of years, looking at moorland mapping burning using Sentinel-2 and moorland grips using LiDAR. Andy's been at Natural England for about 22 years now and has had a varied background, including GIS, species surveillance, biodiversity data mobilisation, and increasingly the application of Earth observation to peat-based applications. So last one of the day, let's hand over to Andy.
Hi, my name's Andy Webb. I work for Natural England and I'm going to talk to you about landscape scale peat mapping, specifically about the England Peat Map project. I'm going to provide an overview describing what it is, the outputs we're aiming to create, why we're doing it and how we're going about it. Now you may notice the logo there. The England Peat Map is part of a larger developing programme within DEFRA called Natural Capital and Ecosystem Assessment, which has got a much wider remit and involves multiple DEFRA network organisations. So what is the England Peat Map? As the slide says, this will be a set of open maps describing the extent, depth and condition of peat in England. We aim to publish all the outputs under open government licence, so they're free and accessible to everyone to use for any purpose. This is not a monitoring programme. It has a finite life of 3 years and is designed to provide improved baseline evidence to support the England Peat Action Plan. So the 4 uses listed there are key ones, but we expect there will be others. I'm now going to go on to describe the key planned outputs on the next few slides. But before I do, it's important just to stress that for all of these, there's no guarantees of success. The work will be innovative, we'll be developing and applying new techniques and data, and many of these will require some research and development, which may lead us to change tack, focus on particular outputs at the expense of others perhaps, or adapt our plans and create different ones. One of our first model outputs we expect to be an England-wide map of peat extent. This is a presence-absence model, and it'll describe areas where we expect peat to occur. We'll create it using a lot of observations of where peat is known to occur, but also where we know it's not. Covariates that we'll use to create the model will include such favourites as soil types, geology, topography and satellite imagery. We'll then create a peat depth model within the areas that are predicted to contain peat. So this will be a regression model now, created using a similar set of covariates, but creating an output of continuously varying peat depth across the landscape within the areas where peat is expected to be present. So it might look a bit like the red image on the slide, but please be aware this is only simulated data, it's not the real thing. We think there are likely to be particular challenges in doing this around the lowlands, where important predictors of depth, such as history of land use and drainage, are rather more difficult to define, whereas in the uplands, depth is more easily predicted from topography, for which we have very good data. The next 3 outputs all describe aspects of peat condition. So firstly, looking at water table depth. There have been a variety of attempts made to predict water table depth in peat using both optical and radar satellite imagery. These have only been done at local site scale and they've faced some significant limitations, such as the depth at which the models perform or confounding effects from vegetation structure or season on the models. But there are also some exciting recent innovations which we're going to explore, such as the application of radar interferometry to peat surface motion. So we may be able to devise an approach that uses a blend of techniques to describe peat condition through its wetness in some form or other. Now, these approaches rely on good ground data as ever, so we will also be working with partners to set up a series of sensors that will help us ensure that the Earth observation data is firmly tied to real-world measurements. Vegetation characteristics and bare peat. So the image shown here is part of the Forest of Bowland, which has been classified into a set of bog condition classes, similar to those that were developed by Moors for the Future. We did this work in partnership with Manchester Metropolitan University, and we're going to build on this to develop new models which predict the types and characteristics of vegetation found on peat. We're initially going to explore options, looking at a variety of approaches such as mapping key species like Calluna or Molinia, as well as condition classes that are described in a variety of ways. Finally, we're going to make extensive use of national LiDAR programme 1 metre data to identify surface features that are important in defining peat condition. The image here shows a sample of LiDAR data, and you can see faint straight lines in the surface there that represent a series of grips. We're developing semi-automated approaches to extracting such features from the data, and so we can overlay on that the grips that we've identified coloured yellow and orange according to estimated depth. So this output used, I should say, a fair amount of manual editing and cleaning to remove noise that we created in the kind of automated processing step of the process. So there are also opportunities to use similar techniques to extract and describe gullies and perhaps other features like peat hags, although the resolution of the LiDAR data is likely to be a key limiting factor. So how are we going to deliver all these outputs? Well, we're going to collate as much existing field survey data as we can with the resources that we've got available. We'll combine that with our own field survey data and use both sources to train and validate the models. We're going to test a variety of machine learning approaches and select those which perform the best. And we'll make extensive use of Earth observation data, particularly from Copernicus Sentinel-1 and 2 missions. We're also going to be on the constant lookout for opportunities to integrate our work with others, particularly internally where site surveys are planned, for example, on SSIs or as part of other monitoring projects. We're going to complete all of this work within 3 years, this being year 1, so we'll finish by March 2024. A little bit more on the data side. We're starting to talk to stakeholders to request access to peat survey data that they have and which we need. I've listed a lot of them on the left there. We're asking for peat depth measurements, dip well data, vegetation quadrats, as well as mapped surface features like grips, ditches, gullies, areas of bare peat and areas of peat hagging. So the image on the right there I've included because it shows that we've already got quite a lot of peat depth measurements in-house. Those are the red dots shown against peaty soils in blue. But you can see from that map that the data we have got is very clustered and there's some areas where we have nothing at all at the moment. On the field survey side of things, our new field survey programme will be based on a sampling strategy which we currently estimate is going to require a few thousand observations across the whole of England. We've been developing a field survey method based around a 10 by 10 metre quadrat, which is shown in the diagram there. And within that, we're going to assess whether peaty soil is present. We'll describe the degree of humification using simple field assessment methods like the von Post test shown in the right-hand picture. We'll measure peat depth at 5 different locations, those are the small circles in the diagram, and record the cover of vegetation using classes or species that are directly relevant to condition and which are likely to be detectable from satellite imagery. We've started testing this method, as in the left-hand picture, and we'll be contracting a significant pilot survey later this year to more fully understand the pros and cons and the changes that we need to make before we embark on a much more extensive field survey programme in the following 2 years. The 2 pink areas on the map there show the pilot areas that we're testing it in this year. So to summarise, the main elements of the proposed work are this year we are setting up and piloting. We're starting to collate existing data, developing our sampling strategy, testing field survey methods and processes, and starting to explore the different aspects of condition that I've outlined, seeing what's likely to work and what's not. In year 2, we'll continue to collect data as we anticipate this is going to take some time. We're going to apply the lessons from piloting our field survey and scale that up considerably, focusing our survey effort on a set of priority areas which have yet to be agreed. This will enable us to create some interim outputs at the end of year 2 for those areas. And we'll also develop our work on condition modelling to build on the research and development, progress with the implementation of approaches that appear most fruitful. And in year 3, we'll complete our field survey in all the remaining regions. We'll complete our extent, depth and condition models and publish our outputs under open government licence. So thank you for listening. I'd like to finish with a call for English peat data. We're very interested in hearing from you if you can supply us with any of the following types of data. So that's peat depth measurements, vegetation survey data conducted on peat, dip well time series data, and mapped grips, gullies, peat hags or areas of bare peat. Please get in touch with us either through the conference or at the email address given below, peatmap@naturalengland.org.uk. So thank you very much.
Thank you, Andy. And that was our last presentation. So in our remaining 14 minutes that we have until our session closes, let's try and answer as many Q&As that you guys have put forward as possible. So to kick us off then, first question, which species cannot be differentiated remotely? Ben, would you like to have a go at this one?
Well, how long have we got? I've got the confusion matrix that Adrian demonstrated earlier, and I could go through this one by one, but I think you'd all be very bored if I did that. It's probably easier to turn the question round. Which species could we map? And one interesting aspect of it, it varies on times of year. So one of the sets of imagery we have was collected in October. Eriophoram angustifolium was quite orange, quite distinct. It mapped well at that point. Not much else did. A photograph in June, Vaccinium myrtillus was a lot greener than everything else, and that mapped quite well. So it's going to be difficult to go through a whole list of species which do and don't map well. I suppose kind of concepts that are worth thinking of. The introduction of the UAV is brilliant. We're now getting centimetre or even lower resolution on the ground. And if you go to an individual plant with that size pixels, you can have a Kaluna plant, some of it's in leaf, some of it's stick, some of it's flower. The same plant can't be different, you know, is different. So there are actually lots of challenges about that. And I think Adrian might want to come in at this point on a sort of more ecologist point of view. Why can't we map some species from remote sensing?
Oh, thanks for
that.
Drop you in it. Yeah, I wasn't ready. Never mind, I'll have a go. I think there's a number of, as Ben has said, phenology is absolutely key. And it's not just phenology, hey, we did the survey in June or October, because all plants don't change on September the 13th. You know, they change spatially all the way across your landscape. So some will be senescing, some will still be in flower, and there's probably some that are still in green leaf. So that's a big, big issue. The second one really is to do with the fact, and this is an old pet of mine, is that all plants are green, pretty much, except when they aren't. And the reality is that we seldom, as ecologists, use green, or as a field ecologist, to identify a plant, because they're kind of, most of them are. What we tend to use actually is a lot of black and white keys to identify the plants through shape and form and morphology and whatever else, and often quite small characteristic shape. So that's one of the crucial things. Yes, we get resolution that's gone down from 30 meters when I was born. It has gone right down now to a few centimeters. You cannot actually see a plant. You can see plants, but you can't see the characteristics necessarily that will identify them unless you go down to millimetre. And that's where you really do. And lots of experiments on this, actually. At what point can a field ecologist tell from a photograph what those species are? And it happens around about the millimetre. So we have a long way to go. Now, I think there's ways of doing this. And I won't go into it now because people get very bored and turn me off, which is fair enough. But yes, we can do a large number of things because some species are, as Ben said, very, very distinctive. Things like Kaluna, Millennia, Eriophyllum at certain times of the year we can do very easily. Obviously, the things you don't want, like bracken, that's straightforward. The smaller species you might imagine are the harder ones to do, and often the minority species in the scene as well. I don't know if that answers the question. Okay.
Brilliant. Thank you very much, Adrian, Ben. In order to try and get as many questions in as we can, let's move swiftly on. So another differentiation question, this time about cutting and burning from satellite data, and how accurate is the quantification of cuts and burns each year? Chris, do you want to have a go at tackling this one first?
Yeah, thanks, Kate. So with our application, we pretty much focused just on burns because it was a case of we knew burns were happening on those sites. So we thought, let's have a look and see if we can figure it out. So I think in terms of comparing that to cutting, I guess you would need to have an element of ground truth into that. In terms of accuracy levels, last time when we checked our burn accuracy, it was at about 89%. So a decent result there, but definitely worth expanding that further, especially having a comparison between cutting and burning. Not something we've done, but something for the to-do list.
Wonderful. Thanks, Chris. Andy, would you like to come in on this?
I would. Thanks, Kate. Yeah. I just wanted to say that we've done a bit of work on this within Natural England with a product we're developing called the Moorland Change Map. And we used a very similar approach to Chris in that we looked at the normalized vegetation difference index before and after burning. And I think in our case, so we were trying to do this over entire landscapes. So again, great point that Chris made about the difference between the sort of scale approach with UAVs at one end and satellites at the other. We were very much at the other, at the whole landscape scale. And I think we found it very difficult to separate burns from cuts using the approach that we were at the time. But I think we're aiming to do better on that through capturing better, more detailed ground data. So I think there is probably more that can be done, but whoever asked the question was right to sort of prod us on it, because it is a very difficult one to distinguish. And that, of course, becomes a very important issue when you're talking about different types of moorland management.
Kate, have you got another second? Can I just throw another
go ahead,
penny worth
Adrian.
in there quickly? We have been doing an awful lot of moorland burn mapping for Natural England and for water utilities. And yes, the pain is, of course, these days, many sites have moved to mowing a block around the outside or mowing a perimeter and then throwing the match in the middle. So in actual fact, what you see is often a combination between a mown strip around the outside and burnt in the middle. So they're not just either or in actual fact. And as we said, separation between the two, frankly, is not easy. Not using remote sensing and not using it at 4 meter resolution. You can do it manually very easily, or fairly easily. But yes, I'm prattling on, so stop me, Kate.
Don't worry, Adrian, I'm sure you'll get another opportunity. It's fine. Thank you very much, Andy, Chris, Adrian, on that one. Okay, another one this time about monitoring change. So can you map different blanket bog states and monitor how these change? Andy, I'm picking on you again.
That's fine, thanks. Again, we've done some work on this in Natural England. We worked with Manchester Metropolitan University a couple of years ago now, using machine learning, remote sensing classification methods on Forest of Bowland initially. And I think you saw, maybe if you can remember, if you were awake, in one of my slides, we had an area of Bowland that was mapped to something approximating a set of bog state classes. And we had mixed success doing that, but we didn't look at change detection. It was a one-off exercise. So some states were, as you might expect, much easier to map than others. And this is something that we aim to pick up and develop further in the England peat map work. I think rather than starting off with a predefined set of classes and saying, well, how well can we do this? How well can we map? How well can we assign pixels or objects to these classes? We might turn it around a bit and say, well, what is Earth observation data most suited to classifying in terms of states? So look at it at sort of the other end of the line, as it were.
Brilliant. Thank you, Andy. Anybody else want to add anything on that one?
Could I just come in? I suppose one challenge always with anything remote sensing is you're seeing the top of the vegetation. Now, what's underneath might actually tell you a lot more about the state of that blanket bog. It might look sort of Kaluna and Eriophorum dominated, but there might be a dense sphagnum carpet underneath. And if you can't pick that up in remote sensing, I'm not convinced you're going to get the best, don't mean to sound negative, the best indication of the state of the bog. I think we know with any remote sensing project, you need ground truth data. No matter what it is you're doing, you've got to be on the ground. So that's my tuppence.
Thank you, Ben. Thank you, Andy. If nobody else wants to come in, I think we'll take the opportunity to move on. We've got 3 minutes left. So let's try a bit of a different one. Can remote sensing, oh, somebody's shot it up and it's gone from my list. Where's it gone? Aha, there it is. Can remote sensing at a landscape scale be used to estimate emissions for greenhouse gases? Could this be used to further refine peatland emission estimates? Now, anybody want to jump in on that one? Don't leave me hanging.
Kate, well, certainly the work that we're doing on the England peat map is designed to support emissions reporting. So, we are aiming to certainly contribute to being able to do that in a better way. But it's a really complicated area of work, and I'm not an expert on the actual mechanics of doing that emissions reporting. That's something that's much more in the realm of UK CEH, who've led on that. But I think the landscape scale models that we'll produce on peat depth will be a really important factor in trying to do that better. I mean, at the moment, there is no kind of national peat depth model for England. So when we have that in place, we'll be able to contribute much more towards a product like, being able to understand the total stock of carbon and how much of that is being lost through emissions each year. But we've got some way to go.
I think I'd add to that as well. It's easy to think about gaseous emissions from peatland. Don't forget the drainage. Don't forget the humic dock. That's why the water looks like tea. I shouldn't, or Coca-Cola, whatever, I can't mention names. But the reason is that's all the carbon, the humic carbon coming out of it. So don't forget, it's not just gaseous.
Brilliant.
Sorry, Kate.
No worries, Adrian. Thank you very much. Anybody else want to come on this? Otherwise, I'll give us one last question. Okay, I'll try and get one last one in. So if national peatland plans are to identify areas for restoration, how will this impact or work alongside other land use practices or development proposals, such as upland agriculture and infrastructure developments such as wind farms? Matt, do you want to have a go at answering that one?
Yes, thanks. I would say the ultimate decision on what activities to carry out, particularly if there are different incompatible options, does rest with the land manager. So ultimately, this is likely to be a financial decision, which depends on which option is most profitable. So of course, This means that the land manager will need to rely on the information that's available in order to determine which option is actually most financially viable. And it'll also depend on the levels of incentivization for different activities. So in Scotland, there's a strong push from the land management community that they should be the ones who gain the financial benefit of any carbon offsetting activities, which peatland restoration lies within for the purposes of this discussion. So this means that the marketisation of carbon offsetting on agricultural land is less likely to be a big thing. So ultimately, the decision on whether or not restoration takes place or something else is going to be influenced by government support and policy.
Brilliant. Thank you very much, Matt. Anybody else want to come in for one last point? Otherwise, I might get shouted at for going over. Nope, no. Okie dokie. I think then that is the end of our session. I'd like to say thank you to all our presenters this afternoon, to Adrian, to Ben, to Chris, to Andy, to Ian and to Matt. Thank you very much for your input today, and thank you to you out there for your questions. I believe all the questions go as part of the on the website for the conference, but so they will be available there. So that's it from us. Thank you very much for tuning in for this session, and enjoy the rest of the conference. Goodbye.